Alright, buckle in folks. I think this is going to be a bit of a longer video because we have to go through some basic science, then we have to do some numerical problems, and we're going to go all the way to a real-world application, so this might take an extra minute. A transformer is a device that can raise or lower the voltage in an electrical wire. Essentially what you have is you have a coil on one end. This is our coil. And that is connected to some sort of power source. I'm going to just draw a battery here. We'll talk later about why that has to be an alternating current source. On the other side, you have a secondary coil that is running off to, let's just say, whatever sort of electrical load resistance that you're trying to power with the different voltage and current that we were talking about. And connecting the two things running through the center is, oop, I screwed that up. Let's try that one more time. Is some sort of temporary magnet. Now, we've discussed in past videos how iron is sort of the most obvious choice here, most commonly used, so this is probably just an iron bar in that U shape. We call this side the primary. We can think of this as the source of our power. We call this end the secondary, and this is our electrical load, or the thing that is using the electrical power. The source, because again we're going to say that it's alternating current like this, is going to turn this part here into an electromagnet. Current will be passing through that wire, and so according to what we discussed earlier, that'll create a magnetic field, and because it's alternating current, that will create a changing magnetic field. So the magnetic field here will go down, and then up, and then down, depending on which part of the, maybe that's the down, that's the up, that's the down. Again, we talked about how to use the right-hand rule to come up with exactly which magnetic field is being created at different points, but for the purpose of this, it really doesn't matter. What does matter is that it's changing, because we can recall from the last video that this coil, the secondary coil, will respond to a changing magnetic field through the law of induction to produce a new current in the secondary coil. So over here we put in an alternating current source that creates an electromagnet. That electromagnet is alternating up and down. That magnet is passed through the temporary magnet to the other side, where now we have a field that's going up and down, and as a result of an induced current is formed in that wire. Now, on both the input and the output side, to actually control this, the voltage that is either going in or out, it doesn't make any difference, is proportional to the number of turns or loops in the coil. What that means then is that if we put in a primary voltage and we want to compare it to the secondary voltage that's going to come out, we can compare the number of coils on the primary side to the number of coils on the secondary side. This is a ratio. We could have written it upside down, or we could put two things on the left, or the voltages on the left and the numbers on the right. It doesn't, or vice versa. It doesn't matter the side. The point is that because it's a direct proportionality, the primary goes to the top primary on the other side, and it's a linear relationship. What that means then is if we want to create something called a step-up transformer, then if we have some sort of voltage being put in, again I'm using this, but it is really an AC source. Step-up transformer wants to have a higher voltage on the secondary coil and a lower voltage on the primary coil. Since these things are directly proportional to the number of turns, what you could do then is you could use a relatively low number of loops or coils on the...
Mr. Armstrong, please call extension 405. Mr. Armstrong, call extension 405.
On the primary and a higher number of coils on the secondary. So maybe this guy's gonna loop a lot more times. And what that means, I put my greater there and less than equal on the wrong side. There you go, like that. So the number of primary is less than the secondary. So since voltage is proportional to the number of turns, what that means then is that the voltage on the secondary side is going to be greater than the voltage in the primary side. That's a step-up transformer. We're going to see later that if you step up the voltage, you effectively step down the current. But I guess they had to call it step-up for either voltage or current, so they used voltage as the sort of definer as to if you're stepping up or stepping down. So the opposite example here, hopefully you can work through this in your own mind then. If you want the output voltage to be lower than the input voltage, then what you're going to do this time is you're going to use a very high number of coils on your primary side. Don't forget your temporary magnet. Going over to your secondary side where you're only going to have a few coils. Because in this case, we want the primary number of coils to be greater than the secondary number of coils, and as a result, the primary voltage to be greater than the secondary voltage. Or we want the voltage to be stepped down in this situation. Now, if we remember that energy needs to be conserved, E in should be equal to E out. Real transformers will lose power to things like heat and stuff like that, but we're just going to pretend it's a perfect transformer. Then what we know is that energy is power times time. And we know the time is the same for primary and secondary. Maybe it's worth making a quick note that by saying this, I am also recognizing that the frequency in is going to be equal to the frequency out. Again, remember, I keep saying that we're using alternating current at all places in this transformer, so that alternating current has a frequency, and that is conserved in the operation of the transformer. So power is equal to current times voltage is equal to current times voltage. This might be the primary side because it's going in. This is the secondary side or coming out. And so what we can get from this is that the multiple of these two things has to remain constant on either side. So if we think about that, if the primary voltage goes up, then to compensate for that, the primary current has to go down. And so a step-up transformer for voltage will be a step-down transformer for current. The ratio, or the product of the two has to remain constant. What that means in terms of a general relationship between the two things is that voltage is inversely proportional to current. As the voltage goes up, the current goes down. To rearrange this equation to see that, I could rearrange it so that all the V's are on one side and all the I's are on the other side. And here I can see the inverse relationship that I'm talking about. Okay, well, let's use these ratios to do a couple of quick questions, and then we'll talk about why these devices are so important for the real world. A step-up transformer has 50 coils, 2,000 coils on the secondary, so NP is 50, and S is what, 2,000? An input signal, primary of 200 volts, and an input current of 0.5 amps. What is the voltage and current of the output? So the easiest thing to do here is to come up with the secondary voltage first, just using the fact that the loops and the voltage are directly proportional to each other. I like when I do these ratio questions to put the thing that I'm looking for on my upper left. It saves me time in solving later. But it doesn't make any difference. If I start with my secondary up on the upper left here, then that means that my number of secondary goes on the upper right, and my primaries are on the bottom. 200. Just putting in the values here. $2,000 divided by 50 is just 40. VS 200, and then VS would work out to 40 times 200, which happens to be 8,000 volts.
Mr. Albano, please call extension 405. Mr. Albano, call extension 405.
So the other thing here is to look at the current. So remember what I said is that the current is inversely proportional to the voltage. Again, in my lazy habit, I'll put the thing that I'm looking for in the upper left. So if my secondary current goes on the upper left, then my secondary voltage must go on the bottom on the other side. Primary current is inverse with primary voltage. So here I've got IS over my input current was 0.5. My primary voltage was 200, and my secondary voltage was 8,000. So 0.5 times 200, 8,000. And I get a secondary current 0.0125 amps, which is a pretty small current, but currents do get to be that small. Okay, secondary numerical example here. We've got a primary current that's coming in at 1 amp. We want it to be coming out at 0.05 amps. We have an original voltage, 20 volts. And we have a primary number of coils of 1,000. The number of coils involved in these transformers, they tend to work better if they have a large number of coils, so they do tend to be large numbers. What we want to know here is the number of coils in the secondary and the voltage in the secondary. So I think I'm going to do these. I don't know what just happened there. I think I'm going to do these in sort of the reverse order they're asked here, because the voltage secondary is fairly easy to find with everything I have. Make it inverse with my secondary current, my primary current, and my primary voltage. So 1 amp, 0.05 amps, voltage secondary, which I don't know, divided by 20 volts. And here, I can just do this math fairly easily. 1 divided by 0.05 times 20 is 400 volts. So now with my primary and secondary voltages, I can find my secondary number of coils. Again, this is a direct relationship, so I'll just set up a direct ratio where my secondary coils is tracking directly to my secondary voltage. Not knowing my number here, I have 1000 on the primary. I have a secondary voltage of 400, and I have a primary voltage of 20, which means I have a 20 there. If I multiply both sides by 1000, and I would see that I need 20,000 coils in my secondary transformer. Just a quick note here, you don't need to do this, you can go in whatever order you want, but if voltage is directly proportional to my number of turnings and voltage is inversely proportional to current, then I can use those two things together to get that my number of turnings is also inversely proportional to my current. If you're trying to remember that, I always think it's pretty easy just to remember that current is the one involved in the two inverse relationships. Okay, so, you know, who cares? Why did we make this fancy thing called a transformer? It was nowhere near as exciting as the transformers from the movies. So perhaps you can explain to me why this matters. Well, if we imagine that most of the electrical energy in this province that's produced it doesn't matter that this video is in Ontario, if that ever matters, but it doesn't matter where you are. Most of the electrical power that's produced isn't produced anywhere near the house where it's actually going to get used. So what that means is that we need to have these huge transmission lines connecting the two things. So all the way to your house. So here's the little power plant that is this is the power plant that is, I guess I'm sort of drawing something that looks more like a coal burning plant, even though I obviously have drawn a waterfall and that's supposed to be hydroelectric plant, whatever. This is where the power is being generated. And this is where it's being used. And these then are our transmission lines. The problem is that while we can make these out of very thick conductors, which will make the resistance of them very low, it's not zero still. Making a superconductive wire to get power to your house just isn't practically too expensive, and so there's some resistance associated with it. What that means then is that as power travels all the way from here to here, then this whole line acts as a resistor. And so power is going to be lost in that resistor according to I squared R. This relationship comes from P equals IV and V equals IR. So when I take the V and I substitute it, I times IR, which gets us as I squared. When we make power over here, the current is going to be very high. And then in this power that we're losing through transmission, current is squared. So that's bad. So what we need to do is, regardless of how we generate the power, when we're transmitting it from one place to the other, we want to make sure the current is very low. What that means then, if the transmission current is low, to avoid the loss that would happen here, right, in transmission. So what we need then is we need some sort of fancy device that has the ability to raise the voltage of something and drop the current of it. Well, thank goodness this whole topic has been on the step-up transformer that has the ability to, say, take a 0.5 amp current and reduce it to 0.0125. Now this is a little tricky because what happens when the current goes very low is that as a result the voltage will go very high. So if that happens, then we have a big issue. It's very dangerous. It's very dangerous to have that high of a current, or voltage I mean, and you can't have that in people's houses because it could shock them and kill them and things like that. So what we do at the beginning of this transmission line is we make a step up transformer. And at the back end here we make a step down. Alright, well I'm going to stop before this music gets going too much. Thanks for listening and sorry for the long video.